All right, in this video is going to be part 2 of section 1.4 dealing with trigonometric functions and their inverses. Okay, so this is going to be part 2 of section 1.4. And that deals with trigonometric functions here. So basically, we're going to look at things like sine, cosine, tangent, cotangent, cosecant, and secant, which are our 6 trigonometric functions and how they are related to the unit circle. Okay, and we'll be finding the value of each expression using the unit circle, and also we're going to be using the coordinate plane to find the remaining 6 trigonometric functions when you're given one of the 6 trigonometric functions. Okay, so when we're dealing with acute angles, the trigonometric functions are defined as ratios of the side of a right triangle. Now, if you're not familiar with what a right triangle is, let me show you on this particular video. Okay, so in this case, let me bring the paper up. You'll see that a right triangle is nothing but a triangle that has a right angle in it. Okay, so here's what a right triangle looks like. And you'll know what a right triangle is because it will have the box at the 90-degree angle. That box does indicate that the angle is automatically 90 degrees. Okay. Also, you need to know something else. The longest side right here, that's opposite that 90-degree angle, we call that the hypotenuse. Okay, and these two sides here and here, those are called legs. Okay. They're called legs here. And also in a right triangle, we can use something that's called the Pythagorean Theorem. All right, so if we have a right triangle, we're going to let this leg be length A, and this leg have a length of B, and the hypotenuse will have a length of C. By the Pythagorean theorem, the square of this hypotenuse, that's going to be C squared, is equal to the sum of the squares of the lengths of these two legs here. That's A squared plus B squared. Now, you've probably seen this before, but that's what we use when we're dealing with a right triangle and we want to find the length of the hypotenuse or even the length of one of these two legs given a hypotenuse and the length of one leg. We can easily find the other. Okay. Now, we're going to be using that in the coordinate plane. Okay. So to extend these definitions to include all angles, we work in a XY coordinate system with a circle of radius r centered at the origin. Okay, so on the next page, you're going to see something that looks like this. Here's a right triangle, and it's centered at the origin. So here's the origin right here at 0 or at O, which is, of course, 0, 0. That's the origin, by the way. And also, standard position means this. If the initial side is on the positive x-axis and its terminal side is the line segment between the origin and that point. Okay. So here's an angle that's in what we call standard position. Okay, because it's on the x-axis. And pretty much if it's on the positive side of the x-axis, I should say, and I'll go ahead and draw this in. Then its initial side would be on the positive x-axis, by the way. And also, if we know the length of x and the length of y, we can apply the Pythagorean theorem to come up with r is equal to the square root of x squared plus y squared. And I'll show you that right now. Because here, this is our Pythagorean theorem, c is equal to a squared plus b squared. Here, the length here is x. So that a will be x squared plus the b is going to be this length here, which is the length of y, so it'll be y squared. And c, of course, is the radius of the circle. The radius is from the center of the circle to a point on the circle. That's the distance. And that's r, so it'll be r squared. Now to solve for r, we just take the square root on both sides. Now we don't include that plus or minus symbol because of the fact that the radius is a distance. And distance is never going to be negative. So it'll be r is equal to just the square root of x squared plus y squared. So that's where that expression came from for r. Okay. Now, on the left side are our 6 trigonometric functions that are related to the right triangle. Okay. Now, these we're going to be seeing more often when we go into the calculus, which is going to be in chapter 2, chapter 3, and chapter 4 from here on out, and in future calculus sequences. Like in this case here, Sin represents the sine of theta. Now, by the way, here they use the Greek letter theta as an angle. Here's a right triangle right here. The side opposite that will be the hypotenuse. The side opposite the angle theta that we're dealing with will be your opposite side. And the angle that's next to it would be your adjacent side. Okay. So Sin represents the sine. So sine of theta is equal to O divided by H. In other words, this angle theta will be the side opposite of angle theta divided by the hypotenuse. So that's where this ratio comes from. Where we have COS, that is the cosine. Cosine of theta. So cosine of theta, here's angle theta here, that would be your adjacent side, this angle, the side next to that angle divided by the hypotenuse. And then for TAN, that is short for tangent. So tangent of theta, that's going to be opposite over the adjacent side. So here, angle theta, opposite side divided by the adjacent side. Okay, now the other three are going to be what we call the reciprocal identities, or the reciprocal functions for the sine, cosine, and tangent. Now here, COT means cotangent. Now for the cotangent, that's going to be the reciprocal of the tangent. As you can see here, tangent is opposite over the adjacent. That would mean that the cotangent will be the adjacent over the opposite side. You can see these two are reciprocals of each other. And now for this SEC, that means secant of angle theta. Now we're going to compare secant with the cosine. Cosine is the adjacent over the hypotenuse. But here the secant is just a reciprocal of the cosine. Hypotenuse over the adjacent side. And then the last one, CSC, means the cosecant of theta. Now let's compare cosecant with the sine. The cosecant of theta is the reciprocal of sine of theta. Here the sine of theta is opposite over the hypotenuse, whereas for the cosecant of theta, it's just going to be its reciprocal, the hypotenuse over the opposite side. Okay. Now later in this section, we'll go into more detail about those reciprocal identities. Okay. But here, pretty much need to be familiar with all 6 of these 6 trigonometric functions. Okay. All right, now let's look at some definitions of trigonometric functions here. Now, those relationships I just gave you dealt with just the right triangle. But let's say that that right triangle is positioned on a unit circle like this. And let's say we let P, which is going to be the ordered pair x comma y, be a point on a circle with a radius of r associated with the angle theta. Then what's going to happen here is sine of theta will be y divided by r. Okay. Now, as you're going to see here, y divided by r, that's the opposite over the hypotenuse. Y is the opposite side, r is the hypotenuse. So it'll be y divided by r. Cosine of theta, since it's adjacent over the hypotenuse, the adjacent side has a length of x. R is the hypotenuse, so it'll be x divided by r. Okay, and then for the tangent of theta, well, tangent, of course, is the opposite side over the adjacent side. So here the opposite over the adjacent would be y divided by x, which is right here. Then the other three, we just take the reciprocal. Like for the cotangent of theta, we take the reciprocal of the tangent theta. Tangent theta is y over x. Its reciprocal will be x over y. And then for secant theta, that's the reciprocal of the cosine. Cosine of theta is x over r, so that means that the secant of theta will be r divided by x. And then finally for the cosecant of theta, that's the reciprocal of the sine of theta, which is y over r. So cosecant of theta will be its reciprocal, r divided by x. Okay, now let's say you were working with the unit circle. And in the unit circle, the radius is going to be equal to 1. So using the fact that the radius is 1 and we're using the unit circle, we just substitute each and every r with 1. So in this case here, if I got sine of theta is equal to y over r, and I'm using that unit circle where r is equal to 1, that means that the sine of theta would just be equal to y, because this will be y over 1 or just y for sine of theta. Cosine theta, x over r. R is equal to 1, so that means cosine theta will be x over 1 or just x. So cosine of theta would be equal to x. Now for tangent theta, is just still be y over x because there's no r in that ratio of y over x. The same holds true for the cosine. There's no r there, so cotangent theta will be x over y. Now for secant of theta, that's r over x, and r is going to be equal to 1, so it'll be 1 over x for the secant of theta using the unit circle. And for the cosecant of x, that's of course 1 over y, since this is r over x and r is equal to 1 over y. Okay. Now, to find the trigonometric functions of the standard angles, which are multiples of 30 degrees and 45 degrees, it is helpful to know the radian measure of those angles and the coordinates of the associated points on the unit circle as given in this on the next page. And this right here represents the unit circle. This right here represents a unit circle. Okay, and I might need to zoom out of this so that way you can see this a little bit better. Okay, that's what the unit circle looks like. Okay. And if you want a better view of that unit circle, I thought I had one, but this is it. This is what that unit circle looks like. Yeah, here it is. Now I'm going to be doing another video explaining how we derive all of these values from that for this unit circle, by the way. So do watch that video. That way you can see where these ordered pairs came from as well. Now, starting with one of these ordered pairs, let's say for 30 degrees, which is pi over 6 in radians, the ordered pair for that would be the square root of 3 over 2 and 1/2. Okay. Now, going back to the fact that sine of theta is equal to y and cosine of theta is equal to x. If that's the case, then that means this first ordered pair, which is of course x, that's actually the cosine. And then the second ordered pair, the second number, which is the y, that has to be the sine. Okay. So your cosine is your x coordinate, your sine is going to be your y coordinate. Okay, so do keep that in mind. All right. And by the way, if you're not familiar with the quadrants that these are in, the upper right is the first quadrant, the upper left is the second quadrant, the lower left is the third quadrant, and the lower right would be the fourth quadrant. Okay. And if you recall, in the first quadrant, both the x and the y coordinates are positive. In the second quadrant, the x coordinate is negative, the y coordinate is positive. And in the third quadrant, both the x and the y coordinates are negative. And in the fourth quadrant, your x coordinate is positive and the y coordinate is negative. And also, I need to mention something about your trig functions, where they're positive and where they're negative. Okay. Now, in the first quadrant, between 0 and 90 degrees, all of your 6 trig functions are positive. All 6 trig functions will be positive in the first quadrant. In the second quadrant, only the sine and the reciprocal function cosecant are positive in that quadrant. And in the third quadrant, only the tangent and its reciprocal function, the cotangent, are positive. And then finally in quadrant 4, between 270 and 360, only the cosine and the secant are positive in that quadrant. Okay, so be pretty much familiar with that unit circle, those 4 quadrants, where it's positive and negative for x and y, and which 6 trig functions in those quadrants are only going to be positive. Okay. And I will have a YouTube video that explains this and how this is derived. Okay. And it's usually derived, by the way, from these standard triangles here. The one on the left is the 45, 45, 90 degree triangle. There are some things that you do need to be familiar with here. All right, because of the fact that these angles are both equal, we also can say that this side and this side, those 2 legs have to be equal as well, which ends up being an isosceles triangle. Okay, so the hypotenuse is, in this case, the length of the unit circle from 0 up to some point. That distance is going to be 1. Okay, now there are some relationships with the 45-45 right triangle. So I'm going to write this off to the side. So for 45 degrees, 90, which is going to be this triangle right here, the length of the hypotenuse, is always going to be equal to the square root of 2 multiplied by the leg, by the length of that leg. It's always going to be that. Okay. So with that square root of 2 over 2, if I was to take the length of that leg, the square root of 2 over 2, multiplied by the square root of 2, I'm going to label this as h. This will be, and this is going to be over 1. The square root of 2 times itself is the square root of 4, but the square root of 4 is 2 over 2, which is 1. That's where the 1 comes from. Now, let's say we want to find the length of that leg. That's going to be equal to the length of the hypotenuse divided by the square root of 2. So if the length of this leg was 1, then, the hypotenuse was 1, then the length of the leg, which I'm going to label as L, that would be the square root of, that would be the hypotenuse, which is 1. So here the length of the hypotenuse is going to be 1 divided by the square root of 2. And of course, we'll have to rationalize the denominator by multiplying the numerator and the denominator by the square root of 2. So 1 times square root of 2 will be the square root of 2. The square root of 2 times itself is going to be 2. So it's 2 over square root of 2. Okay, but now the one on the right is your 30, 60, 90 right triangle. 30, 60, 90 triangle. There's some relationships with that as well. Okay. We have the hypotenuse, which is going to be 1. If I want to find the length of the side that's opposite the 30-degree angle, we have to take 1/2 of the hypotenuse. So this is our short leg. The short leg is always 1/2 the length of the hypotenuse. Okay. And this length right here is the long leg. Okay, and think about this. Let me go back to the length of the short leg. That hypotenuse is 1. 1/2 of that would give us the 1/2. And now for the long leg. If I wanted to find the length of that long leg, I need to do this. Take the square root of 3 times the length of the short leg. Okay. And there's also a relationship here as well. The short leg, if I wanted to find that out, if I know what the length of the long leg is, that would be just the length of the long leg divided by the square root of 3. But for the hypotenuse, there is a relationship for that. If I know the length of the hypotenuse, well, if I want to find the length of the hypotenuse, if I know the length of the short leg, it would be 2 times the length of that short leg. So here, the length of that short leg is 1/2, so the hypotenuse will be twice 1/2, which will just be 1. Okay, so those are just some relationships that you need to be familiar with for the 45, 45, 90 triangle and the 30, 60, 90 triangle. Okay, and I'll be going over more with that on a separate video. Okay. But now we're going to be using this unit circle to help us answer these problems here. So let's say we want to evaluate each expression using a unit circle. Okay, so in this case here, I got the sine of 5 pi over 4. The sine of 5 pi over 4. And I want to find out what the value of that is going to be using the unit circle. And I do need to give you a hint, so I'm going to put this at the top of the page. If you have negative angles, you want to add 2 pi. And anything over 2 pi, you're going to subtract 2 pi each time. And you want to do this until you get an angle that is between 0 and 2 pi. Okay. You want to do that until you get an angle that is between 0 and 2 pi. So let's say, in this case, for sine of 5 pi over 4. Well, 5 pi over 4 is between 0 and 2 pi. Okay, so now I'm going to go back to the unit circle, which is this, and I'm going to find 5 pi over 4. Well, here's 5 pi over 4 right here. And I want the sine of 5 pi over 4. In this case here, I know that's the ordered pair for 5 pi over 4, or 225 degrees. And notice in this case here that your x-coordinate is always the cosine, the y-coordinate is always the sine of that angle. So for the sine of 225 degrees, or 5 pi over 4, it would have to be negative square root of 2 over 2. Okay, so there's our answer right there, negative square root of 2 over 2. Okay, now I could have gotten it from right here as well, because here's 5 pi over 4 right there. The y-coordinate, notice that they have the radical in the denominator, and you may have to rationalize that as well by multiplying the numerator and the denominator by the square root of 2. So here I'm using this unit circle here because of the fact that they've already rationalized the denominator. Okay. Now for the tangent of negative 3 pi over 4. Well, I do have a negative here, so let's do this. If I take that negative 3 pi force and add 2 pi to it, I will get an angle measure that is between 0 and 2 pi that I can easily find the tangent of. Okay, so in this case, let me clear this out. I'm going to leave the pi out when I do this in the calculator. I'm going to do negative 3 divided by 4 and then plus 2. Then press the math key and then number 1 for fraction. Okay, in this case here, I came up with 5 fourths. So that means negative 3 pi fourths plus 2 pi will be 5 pi over 4. So I'm going to be finding the tangent of 5 pi over 4. Okay. Now, here's 5 pi over 4. Now keep in mind, the first, the x-coordinate represents cosine, the y-coordinate is the sine. Okay, but I also know something else, that the tangent, of course, is actually the y coordinate divided by the x coordinate. So in this case, for 225 or 5 pi over 4, the y coordinate is negative square root of 2 over 2. And that's going to be divided by the x coordinate, which is also negative square root of 2 over 2. Well, guess what? Negative square root of 2 over 2 divided by itself. And of course, negative divided by negative is a positive, so it must be equal to 1. So tangent of negative 3 pi force will be 1. Okay. Now part C is the secant of negative pi thirds. Well, again, we have a negative, so let's do this. Bring over the secant, and then negative pi thirds will be added to 2 pi. So it's going to be secant of a positive angle. So in this case here, negative pi thirds, or negative 1 divided by 3, I should say, plus 2. And then change to a fraction, it'll be 5 thirds. So I'm going to be finding the secant of 5 pi over 3. Secant of 5 pi over 3. Well, I know from one of my identities that 5 pi over 3, secant, let's go back to this. Secant is going to be 1 over the x coordinate. So let's find 5 pi over 3. Here it is. And of course, that's always going to be 1 over x, because x represents the cosine of theta. So 1 over that, well, the x coordinate is 1/2, so it would be 1 over 1/2. And 1 over 1/2 means this. I'm going to have 1, and it's divided by 1/2, so that means I'm going to multiply by the reciprocal of 1/2, which is 2 over 1. So 1 times 2 in this case will end up being 2. So the secant of negative pi thirds will end up being 2. All right, part D, sine of negative pi. Secant sine. In this case here, we're going to have the sine of negative pi. Since it's negative, let's add 2 pi. That would mean I'm going to have the sine of 1 pi, or just pi. Okay, let's look on this table right here, on this unit circle. 180, or pi, is right here. The sine is the y coordinate. So what would be the sine here? It'd be 0. The y coordinate there at 180 would be 0, or at pi would be 0. So sine of pi is 0. And next is the secant of 5 pi over 2. Okay, secant of 5 pi over 2 this is over 2 pi, because 5 over 2 is like 2.5. So that's like 2.5 pi. That's over 2 pi. So let's subtract 2 pi from 5 halves. In this case here, 5 divided by 2 minus 2 press the math key, and then number 1 for fraction, that would be 1/2. And that's going to be, in this case, secant of pi over 2. Because that'd be 1/2 pi, which is actually pi over 2. So I'm going to be finding the secant of pi over 2. Now, in this case, secant of pi over 2, the secant in this case is always going to be 1 over the x coordinate. So at pi over 2, which is here, what's my x coordinate here? Is 0. So that means I'm going to have 1 over 0. Because secant is always 1 over the x coordinate. So I know the 1 is in the numerator, but the x coordinate at pi over 2 is 0. But I can't divide by 0 here in this case. So that means the secant of 5 pi over 2 is undefined. Okay? If we recall, division by 0 is undefined. All right, next is the secant of 8 pi over 3. Well, 8 pi over 3, I know that's over 2 pi. So I'm going to subtract 2 pi if I can. So it'd be the sine of, let's see, 8 divided by 3 minus 2. Press the math key in number 1. So 2/3, that's less than 2 pi. So that'd be 2 pi over 3. So I need the sine of 2 pi over 3, which is in this case going to be the y coordinate. Okay, so for 2 pi over 3, that's this right here is 2 pi over 3. The y coordinate for that is the square root of 3 over 2. So the sine of 2 pi over 3 will be the square root of 3 over 2. And then next is the cosecant of negative 11 pi over 3. Here we're looking for the cosecant of negative 11 pi over 3. Well, that's negative, by the way, so let's add 2 pi and try to get a positive angle from that. So it'll be cosecant of, let's see, negative 11 divided by 3 plus 2. Press the math key, number 1 for fraction. I still have a negative, so it'll be negative cosecant of negative 5 pi thirds. Still going to be negative, so I need to add another 2 pi. That's cosecant of the negative 5 thirds plus 2. Okay, that's going to be 1/3. So now 1/3 pi or pi thirds. So now I can find the cosecant of pi over 3. Okay, cosecant, of course, is going to be 1 over y. If we go back here, cosecant is going to be 1 over y. So it's going to be 1 over whatever that y coordinate is at pi over 3. And let's find pi over 3, which is right here, that 60-degree angle. The y coordinate for that is the square root of 3 over 2. So this will be 1 over the square root of 3 over 2, which will be, in this case, the reciprocal of 1 over 3 square root of 2. We just flip the fraction in the denominator over, so it'll be 2 over the square root of 3. And then to rationalize the denominator, we multiply the numerator and the denominator by the square root of 3. And this will end up being 2 square root of 3 over the square root of 3 times itself will be what's underneath that radical without it. So it'll be 2 square root of 3 all over 3. Okay. So this is how we evaluate expressions using that unit circle. Now, again, it's going to take some practice by using that unit circle and also being familiar with these identities here. Okay. And keep in mind that x is always going to be the cosine of x and y would be the cosine of x. Okay. All right, now here we can use right triangles to find the exact value of the remaining trigonometric functions of theta, given one of the trigonometric functions here. All right, and it's also imperative that you know the signs for each quadrant, quadrant 1, quadrant 2, 3, and 4. Because in quadrant 1, both the x and the y are positive. Quadrant 2, only the x is negative, but the y is positive. Quadrant 3, both the x and the y coordinates are negative. Quadrant 4, the x coordinate is positive, the y coordinate is negative. So we're going to start off with part A. Here we want to find the exact trigonometric, well, the exact value of each of the remaining trigonometric functions of theta. We're given in part A that the cosine of theta is equal to negative 7/25. And here theta is in the second quadrant. And I'm going to draw a picture so that way you can see what this looks like. I'm going to draw a coordinate plane. And we're told that this is in quadrant 2. Okay. And also we need to know the relationship here. All right. Cosine of theta is always going to be x over r. And keep in mind that r is always going to be positive no matter what. So the x will have to be either positive or negative. And we're told that theta is going to be in quadrant 2. So if I draw a right triangle in quadrant 2, like this, that would mean that the x value has to be negative. And since cosine is always going to be x over r, that 7 must be negative. So this is going to be negative 7 here. The radius is going to be positive no matter what. That's 25. And in fact, that's the hypotenuse here. All right, so now we need to find out what y is. That's this length going in the upward direction, since 7 has to be negative, and it's in the second quadrant. This is where we use the Pythagorean theorem. And the Pythagorean theorem, if you recall, is this: a squared plus b squared is equal to c squared. Now we're going to substitute this negative 7 for a, that's squared, plus the y, we're going to substitute that for b, so be y squared, equals this radius, which is your hypotenuse, by the way, 25, and that's squared. Now I left the negative sign in front of the 7, so let me include that. But we're going to square the negative anyway, so it's going to be positive, so negative 7 squared would be 49 plus y squared is equal to 25 squared will be 625. That's 25 times 25. So now to find out what y squared is, or to get y squared by itself, we subtract 49 on both sides. That would mean y squared is equal to 576. And to solve for y, we take the square root on both sides of this equation. That would mean y is equal to, if you take the square root of 576, it's going to be 24. And it will have to be a positive 24 since y is in the second quadrant. That would mean the y coordinate has to be positive. Okay, so we know what y is. That's going to be 24. And by the way, this is going to be angle theta, by the way. So now we know what the cosine of theta is. That's negative 7 over 25. We can find the remaining 5. So that means I can find the sine of theta, the cosine of theta. Well, I already know what that is. That's negative 7 over 25. Then tangent theta, cosecant of theta, secant of theta, and finally the cotangent of theta. All right, so now let's find the sine of theta. If this is theta right here, then that means that the sine of theta will be the opposite over the hypotenuse. The opposite side is 24, the hypotenuse is 25. So sine of theta would be 24 over 25. And then the tangent of theta, here's theta, that's going to be opposite over the adjacent side of angle theta. So this will be 24 over negative 7. So that's what tangent of theta is going to be. Now, for the cosecant of theta, I can look at the sine of theta and take the reciprocal, since the sine and the cosecant are reciprocals of each other. So if the sine of theta is 24 over 25, then the cosecant of theta would be 25 over 24. All I do there is just take the reciprocal of the sine. The secant is the reciprocal of the cosine. And the cosine of theta is negative 7 over 25. So that means that the secant of theta will have to be negative 25 over 7. And tangent and cotangent are reciprocals of each other. So if the tangent is negative 24 over 7, then that means that the cotangent will have to be negative 7/24. Okay. All right, now let's look at this example on the next page. Say we got secant of theta is equal to 25 over 7. And here theta is in between 0 and pi over 2. Theta is in between 0 and pi over 2. Well, in that case, this restriction tells me what quadrant this is in. Between 0 and pi over 2 means that it's got to be in quadrant 1. Okay? Has to be in quadrant 1. So I'm going to draw the coordinate plane. And I also know something else. In quadrant 1, all of your 6 trig functions will be positive in that quadrant. All 6 of your trig functions will be positive. Since in quadrant 1, the x coordinate and your y coordinate are going to be positive. All right, so now I need to label which is which. And that's going to be based on the fact that the secant of theta, now let's go back to this, the secant of theta is going to be the radius divided by x, r over x, the radius divided by x, or the hypotenuse here. Radius divided by x. That means this radius has a length of 25. The x has 7, a length of 7. So has to go along the x-axis. So here we're going to find out what y is. Well, I believe we already know what y is from that last example that I did. It's similar. So here, y is going to give you 24. Okay, using that same Pythagorean theorem. Here, the y is going to be 24. Okay. So now we can go ahead and find the remaining 5 trig functions with sine theta, cosine theta, tangent theta, cosecant of theta, We know what secant of theta is. That's 25 over 7. And then the cotangent of theta. Okay, we'll start with the sine, cosine, and tangent. And then take their reciprocals to find the other two here. For sine of theta, and here's theta right here. Sine of theta is always the opposite side over the hypotenuse. So here, this will be 24 over 25. And then the cosine of theta, that would be adjacent over the hypotenuse. So that's going to be 7 over 25. Tangent of theta will be the opposite over the adjacent side. So that's going to be 24 over 7. And then we can get the reciprocals of each one of those. Like for the cosecant of theta, the reciprocal of 24 over 25 for the sine of theta will just be 25 over 24. Cotangent of theta is the reciprocal of the tangent. So if the tangent of theta is 24 over 7, then that means that the cotangent will have to be 7 over 24. Okay. All right, part C looks like this. The cosecant of theta is 41 over 40, and theta is in between 0 and pi over 2. Well, just like in that last example, 0 to pi over 2 means that our angle is going to be in quadrant 1. Quadrant 1. And in quadrant 1, again, all 6 of your trig functions will be positive. Okay. All 6 of your trig functions will be positive. So I'm going to draw a right triangle. Here's a right triangle. Here's theta. All right, so cosecant is the reciprocal of the sine. But I'm going to look for the cosecant. That's going to be, of course, 1 over y. Or I should say, for the cosecant, r over y. R over y. The radius divided by the y. So that's r, and this is going to be y. So that r is going to be the 41. That's going to go here. The y, which is your 40, that has to go here because y goes up. And now we need to find out what this length is, which is going to be x. Okay, so that's where we use the Pythagorean theorem. A squared plus b squared is equal to c squared. Now the a, of course, will be 4. Well, actually, let's let a be what x is. So x squared is what we're looking for, plus this is b, 40 squared, is equal to the hypotenuse, 41 squared. The radius and the hypotenuse are going to be the same thing here. So now, let's simplify this. We got x squared is equal to 40 squared, that's 1600, equals to 41 squared, which is 1681. And then to solve for x, we subtract 1600 on both sides to get x squared is equal to 81. And then to find out what x is, we take the square root on both sides of that equation. And it's going to be x is equal to a positive 9. Since we're in the first quadrant, both the x and the y are going to be positive. So that means this side on the x-axis is going to be 9. Okay, so now we can find the sine of theta, cosine theta, tangent theta, Cosecant of theta, we already know that's 41 over 40. Because that's given to us. I wrote that all wrong. CSC for cosecant of theta. 41 over 40. Secant is what we're trying to find, and then cotangent of theta. Okay, so now let's start with the sine of theta. That's going to be the opposite side over the hypotenuse, which will be 40 over 41. And then for the cosine of theta, here's theta. That's the adjacent side over the hypotenuse, 9 over 41. And then for the tangent of theta, that would be opposite side over the adjacent. That'd be 40 over 9. Cosecant of theta, that's 41 over 40. The secant is just the reciprocal of the cosine. Since the cosine is 9 over 41, the secant will have to be just 41 over 9. And then for the cotangent of theta, well, tangent of theta is 40 over 9. So cotangent is the reciprocal of the tangent, 9 over 40. And there you have it. All right, part D looks like this. The tangent of alpha, and that's the Greek letter alpha that's also used in angle notation. Tangent of alpha is equal to 1/5. And alpha is between 0 and pi over 2. So that means that angle is in quadrant 1 based on that restriction. So that means all 6 of your trig functions in quadrant 1 will be positive. All 6 of your trig functions are going to be positive. So here I'm going to draw a right triangle. Keep in mind, these angles are not drawn to scale. So here's theta. Now, if you recall, the tangent is always going to be opposite over the adjacent side. So the opposite side of theta will be 1. The adjacent side of angle theta will be 5. So here we need to find out what R is. Using the Pythagorean theorem, we got a squared plus b squared is equal to c squared. Here, my a is going to be equal to 5 squared plus b is going to be 1, and that will be squared is equal to r squared, which is what I'm trying to find. 5 squared is 25. 1 squared will be 1, and that's equal to r squared. 1 plus 25 will be 26. That's equal to r squared. And to find out what r is, we take the square root on both sides. So that means r is equal to the square root of 26. And I will simplify that no further. So that's my hypotenuse there in that triangle. R is equal to the square root of 26. All right, so now we can find the remaining 5. Sine of theta, cosine theta. We already know what tangent, well, let's say tangent of alpha. And so using theta, I forgot that the angle measure was alpha. So let's be consistent here. That's alpha. This is alpha. That's alpha. Tangent of alpha was 1/5. That's given to us. So here I can find the cosecant of alpha, secant of alpha, and cotangent of alpha. All right, now sine of alpha is this, opposite over the hypotenuse. That would be 1 over the square root of 26. But of course, we can't leave the square root in the denominator, so that means I need to multiply the numerator and the denominator by 26. So 1 times the square root of 26 will be the square root of 26 over the square root of 26 times itself will be that number without that radical. It just be 26. So I have the square root of 26 over 26. And then the cosine of alpha, well, here's alpha right here. That's adjacent over the hypotenuse, 5 over the square root of 26. 5 over the square root of 26. And in this case, I can't leave the square root of 26 in the denominator, so we do rationalize again by dividing the numerator and the denominator by 26. So this will be 5 square root of 26 all over 26. And now for the cosecant of alpha. All right, that would be the reciprocal of the sine. And I'm going to use that 1 over the square root of 26 and take its reciprocal. So it'll be the square root of 26 over 1, which is the square root of 26. Notice I'm not using this right here because I have to rationalize that denominator again. It'll be best to use this fraction before I rationalize the denominator and take that reciprocal. And I'll do the same for the secant. Take the reciprocal of the cosine of alpha, which is 5 over the square root of 26. When I do the reciprocal, the square root of 26 will be in the numerator, the 5 will be in the denominator. That's all there is to it. And then the cotangent of alpha, that's the reciprocal of the tangent of alpha. That's 1/5. The reciprocal of that would be 5 over 1, which is just simply going to be 5. Okay. So that's how we find the remaining 5 trig functions when we're given what one of them is and the restrictions on the quadrant that it's in. All right, here's one more of this. Let's say I want to find the well, I'm given the cosine of alpha is equal to the square root of 2 over 3. And this time, alpha is in quadrant 3. Now I want to find the remaining 5 trigonometric functions. So now let's see what this looks like when I put it in quadrant 3. All right. So here's what the triangle will look like. Because in quadrant 3, I know that the x will be negative and the y will be negative. And this is alpha. And this is a right triangle here. I know for the cosine, it has to be the adjacent side over the hypotenuse. So that numerator is the square root of 2, that's the adjacent side. But if it's in the third quadrant, that means that that x coordinate will have to be negative. So that means the square root of 2 will have to be negative. So I get negative square root of 2 here. The hypotenuse is always going to be positive. It's going to be 3. Now I need to find the length of this side right here, which is going to be the y. And I'm going to be using the Pythagorean theorem in this case. So the a squared plus b squared is equal to c squared. And in this case, the a will be that negative square root of 2. Negative square root of 2 would be squared, plus the y would be b. So I'm just going to say y squared is equal to c, which is that hypotenuse or the radius, 3 squared. All right, if I square a negative, that's going to be positive. The square root of 2, you turn around and square it, that's going to knock that radical out, leaving you with what's underneath it. It'll be 2 plus y squared equals 3 squared, or 3 times 3, which is 9. And then we get y squared by itself by subtracting 2 on both sides. That would mean y squared is equal to 7. And then if I take the square root on both sides, that would mean y is equal to the square root of 7. However, notice in this figure that I drew that we're in the third quadrant. That would mean not only the x will be negative, the y has to be negative. Has to be, because it's in the third quadrant. Both the x and the y coordinates are negative. So that means y has to be negative square root of 7. Right, now, from this, we can find the remaining 6 trigonometric functions here. Let's see, starting with sine of sine of alpha. Cosine of alpha, we already know, that's negative square root of 2 over 3. Tangent of alpha, cosecant of alpha, secant of alpha, and cotangent of alpha. All right, so now sine of alpha, here it is right here. That's going to be the opposite side over the hypotenuse. That would be negative square root of 7 over 3. And then for the tangent of alpha, that's going to be the opposite side over the adjacent side. Here, the opposite is negative square root of 7 over the adjacent side, which is negative square root of 2. Well, in this case, negative divided by negative will be a positive, but I cannot leave that radical 2 in the denominator, so I need to multiply the numerator and the denominator by the square root of 2. Now, we can multiply underneath these radicals here as long as the indices are the same. So the square root of 7 times the square root of 2 will be the square root of 14, divided by the square root of 2 times itself will end up being 2. So tangent of alpha will simplify as the square root of 14 over 2. Now for the cosecant. Well, the cosecant is the reciprocal of the sine. So all I need to do there is just flip this over, bring the negative over. So this will be negative 3 over the square root of 7. Now I got the square root of 7 in the denominator, so I need to multiply the numerator and the denominator by the square root of 7. So negative 3 times square root of 7 will be negative 3 square root of 7 over the square root of 7 times itself will be 7. And then for the secant, that's the reciprocal of the cosine. And let me bring this down a bit, so I have room to write all of this. All right, this secant of alpha, the reciprocal of the cosine, which is negative 2 square root of 3, I'll flip that over, it will be negative 3 square root of 2. And to get rid of the radical in the denominator, I'll multiply the numerator and the denominator by the square root of 2. So it'd be negative 3 square root of 2 over square root of 2 times itself would be 2. And then finally, the cotangent of alpha. Cotangent of alpha, well, let's look at the tangent here in this case. I could use this negative square root of 7 over negative square root of 2 and take its reciprocal. So that'd be like negative 2 negative square root of 2 over negative square root of 7. And I got that square root of 7 in the denominator, so I need to multiply the numerator and the denominator by the square root of 7. Negative divided by negative will be positive, by the way. Square root of 2 times the square root of 7 would be the square root of 14 over the square root of 7 times itself would be 7. So I end up with 14 negative, well, just the square root of 14 over 7. Okay. So this is one of those cases where you have to make sure that you label the y as either positive or negative, depending upon what quadrant that angle is going to be in. Okay. All right, so that's going to conclude part 2 of section 1.4, dealing with trigonometric functions and their inverses. There is a part 2 homework assignment for that. So make sure you do complete that, and feel free to ask any questions by email or stop by after class if you have any questions about what's in this video and also what's in the homework.